When we talk about artificial intelligence, it helps to set aside the science fiction tropes of conscious, brooding machines. In practice, modern AI is built around rational agents. These systems take in information from their surroundings and make choices that maximize a beneficial outcome. To build a rational agent, engineers define how it interacts with the world using a framework called P's. That stands for performance, environment, actuators, and sensors. The environment variable is where things get complicated. A delivery drone isn't operating in a vacuum. It has to navigate rain, heavy traffic, and unpredictable physical obstacles, all of which create a highly unstable data landscape. This real-world environment imposes 3 strict limitations. First, it is partially observable. The drone's sensors cannot see everything, like a pedestrian hidden behind a truck. Second, it is non-deterministic. An action, like braking, doesn't always guarantee a perfect stop on wet pavement. Third, it is dynamic, meaning the world keeps changing while the machine is trying to decide what to do next. The central challenge of modern computer science is building an agent that can process that chaotic, incomplete reality and still successfully execute its objective. To solve that problem, engineers developed a ladder of increasingly sophisticated agent architectures. The baseline tier is the reflex agent. This system operates entirely on rigid condition-action rules. Think of a basic robotic vacuum. If its sensor detects dirt, it triggers an action to activate the suction. It has no memory of where it has been and no overarching concept of the task it is performing. It simply reacts to immediate triggers. That knee-jerk reaction fails the moment the environment gets complicated. To fix this, engineers upgrade the system into a goal-based agent. Now, the machine understands a desired end state, like recognizing when the entire floor is clean, and selects actions specifically to reach that finish line. But completing a goal isn't always enough. We care about efficiency. The next step up is the utility-based agent. This adds an internal performance metric, called a utility function, to judge exactly how well the goal is being achieved. Instead of just cleaning the floor, it measures success by reducing dust to less than 1 million particles per square meter, constantly evaluating its own effectiveness. Defining a strict goal and measuring utility provides a strong foundation. However, the agent remains useless if it lacks the computational ability to map out the physical steps required to get there. This is where search algorithms come in. A search algorithm is the mathematical process an agent uses to find a path from its current starting state to its final goal. An uninformed search algorithm blindly checks every possible path until it stumbles into the solution. In vast environments, that wastes enormous amounts of time and memory. Informed search algorithms solve this by leveraging domain-specific information to move directly toward a solution. That information is expressed as a heuristic. A heuristic is an estimation of the distance remaining to the destination, a strategic value that directs the algorithm toward promising states faster. This chart shows a map of Romanian cities to demonstrate how an informed search algorithm navigates. The numbers along the solid lines are actual travel costs, while numbers in brackets are straight-line distance estimates to the goal of Bucharest. A* calculates the optimal route by adding the actual distance traveled to the heuristic estimation. By comparing these combined scores, it avoids dead ends entirely and locks onto the path through Sibiu, Râmnicu Vâlcea, and Pitești, achieving the lowest possible travel cost of 418. Heuristics are critical for real-world AI. By cutting through millions of useless variables, they save vast amounts of computational time, allowing machines to make complex routing decisions instantly. Even with perfect routing, a dynamic environment will inevitably throw unmapped surprises at the agent. To survive the unexpected, the machine requires the highest tier of architecture, the learning agent. This diagram outlines how a learning agent operates. The process starts here, at the performance element, which takes in sensor data and selects the actual physical actions the robot will perform. As the agent acts, a separate internal system called the critic observes the results. The critic compares the agent's actual performance against a strict baseline standard and passes that evaluation down as feedback. That feedback flows directly into the learning element. If the critic determines an action was inefficient, the learning element permanently upgrades the rules inside the performance element, ensuring the machine makes a better choice next time. The most counterintuitive part of this design is the problem generator. Its sole purpose is to occasionally force the AI to try unusual, exploratory, or suboptimal actions. By making mistakes on purpose, the agent gains new experiences and discovers shortcuts it would have otherwise ignored. This continuous loop of action, critique, and adjustment gives the system true adaptability. It allows the machine to step outside its original programming and adapt to variables its creators never anticipated. When you order a meal and watch a delivery drone land on your driveway, you are watching this entire architecture fire at once. The drone gathers percepts through its sensors, applies heuristic algorithms to calculate the fastest route, processes unexpected wind speeds through its learning loop, and executes the exact physical thrust required to land safely. This structure transforms artificial intelligence into a highly efficient mathematical tool designed to rationally navigate the same messy, unpredictable reality that humans do.